First of all, I would like to thank the organizers, Patrick, Raphael, Piotr and Evelina for this kind invitation. It's always a pleasure to be in Lumini or in MathFlows conferences in general, since they're organized in different places. So today I would like to talk about Rayleigh-Bénard problem in the framework of compressible fluids. But Rayleigh-Bénard problem is well, an example of generally the whole idea of open systems, meaning energetically open systems, that recently is quite often studied. So this is also quite a new topic for me. The first time I'm going to talk about this here. Okay, so let me maybe introduce you some. So generally, this energetically open systems, they are interesting. One thing is that they really capture different phenomena that we can observe in nature, including the convection problem that I will mention in a moment. But also it is interesting. This kind of approach is interesting from the point of view of description of turbulence, which I will try to motivate a little bit later. So Bénard-Rayleigh problem. What is happening there? So we have a fluid between two parallel plates, and we heat the fluid from the bottom and we cool it from above. So what is happening? Well, you may expect creation of such a convection cells. If you think about applications where you can get, well, there are wide applications: meteorology, oceanography, some well, cellular problems and so on, magnetodynamical problems and so on. Okay, so some remarks about the literature about asymptotic. Did I jump something? No. Okay. About the literature on this problem. So what is quite often you can see in the literature is Rayleigh-Bénard, but in a little bit simplified setting. So not in the full compressible system, but in the incompressible framework. One considers Oberberg-Boussinesq approximation. So I mentioned a couple of papers here, but of course the literature is much more wide. So also quite recent studies of the group of Felix Otto, Camilla Nobili, and other collaborators who concentrate also in the setting of Oberberg-Boussinesq system, concentrating some scaling laws there. Okay, so but what will be interesting for me is the full Navier-Stokes Fourier system. So we include the mass density, the temperature, and the velocity. So the standard system, well, P is of course for the pressure, specific internal energy, viscous stress tensor. Well, as what is typical for this case, we have the gravitational potential, but the issue whether this mechanical force is in the potential form or not, I will be touching this topic because it some places it will have some meaning. Well, the heat flux, and this is standard. Okay, so I as I mentioned, this Rayleigh-Bénard problem is some paradigm for this open system. So I will only concentrate on that here. However, one could consider more general conditions with some inflow and outflow of the velocity. So we assume that we have periodic boundary conditions with respect to horizontal variables. Velocity is equal on the 0 on in the x3 equal to 0 and 1. And what we mentioned here, the bottom the bottom temperature will be denoted by theta b and upper temperature with theta u. So intuitively, so we have two given quantities. I assume for simplicity they are constant, but they can be some functions. The fluid is Newtonian, and the heat flux is given by Fourier's law. So this is nothing, everything standard here. Okay, so few words about energetically closed systems. So we have one would have impermeability boundary conditions or no slip boundary conditions, and what is typical that there are homogeneous Neumann boundary conditions for the temperature. So we have the information on the flux on the boundary. So there is a vast literature again in this topic. So as a summary, one can mention the monograph by Rayleigh and Novotny, but of course this would be impossible to give the list of for people who are working on this. Okay, and still about energetically closed system, because what I'm the direction that I want to follow to get, I would like to talk about asymptotic behavior of solutions. So what happens in the long run? So for energetically closed system, it's quite well understood already, and this is the situation is. One could say a little bit boring, because what may happen if you have the mechanical force in potential form, then all solutions tend to equilibrium. But this is not. If this is not the case, then one can show that the energy tends to infinity for any weak solution. Yeah. So that's why it's seen that it's not the best. No space really to describe some turbulent behavior in the long run. Okay, so for that we can see some the papers of Reisel, Braszak, and Petzeltabau in some different combination of these three authors. So the recent studies for the energetically open system, not necessarily only for the Rayleigh-Bénard problem. One thing is the studies of Reisel and Novotny, and the later of Nielasis, Kauduri, and Reisel. This is in fact the result that Nielasis will talk today in the afternoon. So I would like to advertise his talk and make a short complaint to the organizers that our talk is not in the opposite order. So anyway, I will have to mention a little bit about the existence of weak solutions, but I will try to do it at least as possible, not to destroy Nielasis' talk. So anyway, this result is interesting for me and meaningful because here. You get the Dirichlet, inhomogeneous Dirichlet boundary conditions for the temperature. And also some collections of many ideas you can find also in the recent monograph by Edward and Novotny. The monograph which was published very recently, I think. Well, surely already after Antonin passed away. Okay, so few words about these weak solutions, because I cannot pass to asymptotic behavior without that. So the concept of weak solution for the Navier-Stokes Fourier here with Rayleigh-Bénard problem for the Navier-Stokes Fourier system. I underline it because it's important that we have here this inhomogeneous boundary conditions for the temperature. So this is the combination of energy inequality and ballistic energy balance. What exactly I mean by this, it will appear in the next slides. With the conservative boundary conditions, this energy balance was like an integral part of the solution, of the definition of weak solution. So now it is in fact replaced by the ballistic energy balance. And what is the reason for that? The point is that on the boundary we control the temperature and not the flux. So if you look at the evolution of ballistic energy, you will see that you can express it, in fact, only in terms of the control it in terms of the boundary values. Okay. So we'll say that density, temperature, and velocity is a weak solution on the time interval t infinity. Of course, I'm interested on this time interval because of this long time asymptotic that I have in mind. The existence result is on some time 0t for any t, but extending it for t infinity is quite straightforward. Okay, so the regularities of solutions, I will not concentrate on this. I will leave it to Nilasis. And well, of course, continuity equation together with also its renormalization property, which is very much needed for estimates on the density later and for the compactness of the density. Momentum equation, okay, this we expect. As entropy inequality, that's what we are used to also in case of compressible fluids. Here this S here, the quantity S is an entropy which is related through Gibbs equation, and this ballistic energy balance. So what this quantity what you see here is the ballistic energy. What you don't recognize from the previous slides is the quantity theta tilde, which is we take our boundary data and we extend it to the function, to the C1 function on the whole domain. Okay. So this we are fine with weak solutions with this ballistic energy framework. There is global existence with strong uniqueness, compatibility. So that's already a nice notion. Good basis for me to start. Good. So, and what about uniqueness? Well, it may happen that solutions are not unique. Anyway, we don't have the proof of uniqueness. So that's why, if you think about attractors in such a very standard approach, like for dynamical systems, based on the concept of solution semigroup, so this is not directly applicable, but we go the different way. So as you will see, we use the statistical description based on Krylov-Bogolubov theory, and we will be generating a measure on the space of entire solutions for the Navier-Stokes Fourier system. And so we will not really look at the at the phase space, but we'll look at the space of trajectories. This is not an innovative idea to look at the space of trajectories. If you look at the old papers of Sell and Malek and Nechas, they also had this approach. Okay. So before I get to the theorems, which are a little bit long and take the whole slide and require quite a lot of estimates, which don't worry, I will not present you here. But anyway, I will start with some short itinerary that you get on 2 slides that you have the whole concept of the talk. Well, one is to identify some suitable class of initial boundary data that give rise to solution with globally bounded energy. So the important thing that is that this bound on the energy, well, I wrote here initial boundary data, but this bound depends only on the boundary data. So our quantities, this theta B and theta U, these apparent lower temperatures, and the mechanical force. So in our case, this gravitational potential. Okay, so if we are able to show that such a bound exists, and we are, we can claim that the system admits a bounded absorbing set. So. So we can think about such a omega limit set. However, well, the meaning here in our setting is slightly different than in the standard way. Let me try to specify it a little bit. So not like in the standard definition here. It is a subset of the space of entire trajectories. That tracks the time shifts of a given solution, yeah, local in time. So what basically may happen that one could expect different global in time solutions will share the same omega limit set. And on the other hand, on one hand, and on the other hand, that we cannot exclude that there will exist many omega sets. Anyway, so what we will show that this omega limit set generated by this bounded solution, I mean in sense of this, that energy is bounded, this is non-empty, and it consists entire solutions of Navier-Stokes system. For this to claim, we will need the asymptotical compactness of solutions, but I will spend some time on this. So what we mean that the approach compact set in the phase space when we let t going to infinity. So basically this is the plan for what I'm going to present you. Okay, so what the result that appeared also this year by Fayese and Kwon, who also studied asymptotical stability of solutions to Navier-Stokes Fourier system, also with inhomogeneous Dirichlet boundary. So let me maybe now try to formulate more precisely what I was only describing in words on the previous slide, and then I will show you what will be different in the problem that we consider. So. So always when I mention Levinson dissipativity, I mean that global boundedness of trajectories and existence of bounded absorbing set. So to write it clearly, we say that Navier-Stokes Fourier system is Levinson dissipative if there exists a universal constant, I call it E infinity, such that for any weak solution, this quantity is bounded. And this EB here, this is this ballistic energy, which is here the energy, this is standard energy, minus the following term. This theta bar, I will remind you, this is this extension of the boundary function for the whole set. Okay. So the point is that in this paper the authors introduced the hard sphere perturbation of the equation of state. So so they add in the equation of state there's additional term which well it's not only that it appears here, it used in some works before. Anyway, maybe I will not recall it exactly, but concentrate on what effect it gives. Well, it gives the uniform bound imposed on the fluid density. So that's for any weak solutions, which is something that simplifies a lot the situation. So in the recent paper with Edward, we abandoned the hard pressure component and show the Levinson dissipativity, as I mentioned. So as we relax the hard sphere pressure, and we also consider physically relevant equation of state of a general monatomic gas with the exponent. I made some slide on the details of this pressure to the end. I don't want to put it here because I thought that maybe no one would be interested so much in the exponents except of Evelina for sure. But let me just not go to details and come back to this later. And this asymptotic compactness that I mentioned, that any bounded family of global solutions is precompact in suitable topology of the trajectory space. Okay, some water. Okay, so consider the Rayleigh-Bénard problem. So Rayleigh-Bénard problem, of course, for Navier-Stokes Fourier system, and under the assumption that all the assumptions for the equation, constitutive relations and so on for the coefficients. I'm not going to put them on slides. So anyway, there exists this constant universal which depends on the boundary data and the total mass of the fluid, such that any global in time weak solution defined on this set satisfies this estimate. So I don't remember whether I put on the slides or maybe I will put it on, give it on the blackboard. There's once we what we can show is the bound for the ballistic energy, but from the bound of the ballistic energy we can pass to the bound of the for the energy when times goes to 0. And more, even more, if we can say that this we can have uniformly for all the solutions, then the convergence is uniform in well for the solutions. Okay, this is for if we go to t to at certain time t, then it is uniformly bounded for larger t. And asymptotic compactness, what I mean by that. So I look at the sequence of solutions. By that I mean this index n is related with the time interval prescribed on Tn to infinity, and with Tn we pass to the minus infinity. So we want to have it on the whole real line. So such that this energy is uniformly bounded. Then we can claim compactness. So we can well, the convergence of theta n and un. This is basically we follow here what is done for weak solutions. What needs more attention is the velocity, the density. For that, you have to do some work. Okay, and this limit solution is again bounded in the context of energy. So these two things are really one you have to prove, but then you have a lot of let's say benefits. Existence of compact trajectory attractor invariant measures, existence of stationary statistical solutions, and information on the ergodic averages. So okay, before so I will go through these points, and these are interesting questions when you look at think about the theory of turbulence and what people are interested in, and especially the issue of convergence of ergodic waves is the question that many would ask themselves. Okay, I'm too slow. Good. So let me introduce the trajectory space. Okay, so what would the object that we have in the definition of weak solutions, rho theta u, would be natural, but okay, but these are not the conserved quantities. So, and we would like to have well-defined values for any time. So that's why we jump to rho, to the total entropy, and to momentum. This is natural from the equations. So we defined this space as a union of TLs. So okay, so this will be the following set. So you slightly well, it's larger space than we have from the estimates. This is because the later for the later application when we will want to define some random processes. Anyway, so the definition is based on some partially continuous here functions and Caglat, so left continuous functions. This is of course related that we have continuity equation, momentum equation, and entropy inequality, not equality. Okay, so so this I mentioned because of this not clear fact of uniqueness. We replace the standard phase space by this trajectory space, and we define the following set A. This is rho SM, so it's a weak solution of the Navier-Stokes Fourier system on time interval, and the energy is bounded. And this is a good candidate for the global attractor in the trajectory space. Okay, so so one thing that I mentioned, that this set A is a subset of this for sufficiently large this TL, and is a subset of the trajectory space. So what we can show? We can show that this set is non-empty. This is time shift invariant. So it means that if this belongs to the set, then for any t, this will also belong. And this is compact in metric topology for a sufficiently large L. So we will introduce, this will be the complete metric space with appropriate metric. Do I put it on the slide? No, I'm sorry, I don't remember what I put exactly in the slides. Anyway, we have the metrizable topology, so this nothing surprises with this metric how we define it, and then we are ready to define to claim the existence of trajectory attractor. So if we denote by F a family of weak solutions with mass equal to m, and with that condition, then we identify this set with the subset of trajectory space, extending them by constant values for negative times. And then we have the convergence in appropriate metric. Okay, and good. So the next conclusion that we can have is about the statistical solutions. So these are invariant probability measures on this space T, the space of trajectories, which are supported by the solutions of Navier-Stokes to the Navier-Stokes Fourier system. This is, well, the construction is the same as in the paper of Francesco and somewhere and Edward and Martina Hoffmanova. And also similar approach you can find for incompressible setting. So let me specify what I mean. So if I have a trajectory rho SM, we consider the probability measure. Here is of course the Dirac measure defined as follows, such a time average. This is of course the probability measure. Then if this is an element of the set A, then this is this object belongs to the set of probability measures on a compact Polish space. This Polish space is the space of trajectories plus appropriate metric. In particular, this family is tight. So what we can conclude? We can conclude there is a sequence of times such that this sequence converges narrowly in the space of these probability measures. What else? The measure is time shift invariant. So it means that this relation holds for any Borel set. And this limiting object this is what we call statistical stationary solution of the Rayleigh-Bénard problem. So, so let us summarize it in a theorem. So we can claim, well, for any subset of A, which is non-empty time shift invariant set, this we already know, that there exists a stationary statistical solution which is supported by U. This will mean is compact in compact metric space. This is a Borel probability measure. Support is in U, closure of U, and this is shift invariant. So that's what's quite fast conclusion. And what about ergodic averages? So let's this is again, the tools are ready for this. We use Kirchhoff-Khinchin ergodic theorem, so we consider the following separable Hilbert space. We take the statistical stationary solution, which we constructed, and consider such a probability space. Yes, T is the trajectory space, family of Borel sets, and we take the given trajectory and we make define such an associated canonical process. Yes. As this measure is shift invariant, then the above process, this is a stationary process with respect to this probability space for tau, with again Kaglad paths in H. So knowing that, what can we say? We can say that for any Borel measurable function, yes, for which this in zero this is bounded, there exists a measurable function f such that these averages converge to f as time goes to infinity, almost surely, and an inner one. Okay, so I have a couple of minutes. Yeah. Okay, very good. So that's the story of this asymptotic things that you can conclude from appropriate bounds. One topic that I would like to also mention, which was like a follow-up after this studies on the long term, is the question whether there exist time periodic solutions for the system. This is the next common paper with Edward, but here with Piotr also, Piotr Gwiazda. So we took not necessarily Rayleigh-Bénard problem, but problem with such a Dirichlet boundary data for the temperature, which are periodic, and the mechanical force is periodic. Temperature is bounded from below. Then we show that there exists at least one periodic solution with the total mass bounded. Here, what this by ST? Sorry, there are too many S in my talk. However, this is just such a periodic flat sphere. So I don't want to present any details about these results, but what I would like to mention, anyway, some approximation for this open for this system where we don't have given flux on the boundary. We use the paper of Piotr Mucha and Edward Feiereisel, and I forgot, sorry, who was also co-author there. Anyway, the bounds that we consider the driving force, let's call it rho g. We assume that this is in potential form here, which is of course physically relevant because lots of forces are in the potential form. However, if you think about some periodic situations, you would like to have the fluid which is stirred up in some container, and this is the case that this potential case would not work. So we were thinking whether we can handle non-potential forces. So what we see immediately is that it could be improved to non-potential forces in two-dimensional case, and then benefit from the Sobolev embedding. And another situation is that if we know the total mass is small, then also small with respect to this amplitude of g, then again we could get, but general force in non-potential form. This we didn't know how to handle. Okay, so yeah, about the pressure, but I think I will skip it. Only wanted to underline that a good example for our pressure is like rho to the power 5/3 plus theta to the power 4. This 5/3 is a nice exponent, and we're happy to have it, not something strictly smaller than 5/3. Okay, so thank you very much for attention.